Continue on here. I have the remaining exams I'll pass back during a break, before we go to break. But as far as the exams go, you want to think about how you can memorize things like nomenclature and that kind of stuff. You know, what kind of techniques do you use to memorize? Or do you not have enough time? You know, if you're struggling with the memorization for the nomenclature, think about, or maybe do a search and see what other people do to memorize things. Because the next test, if you don't know the formulas and the names, you'll end up losing a lot of points on the chemical reactions part, the redox part. So try to get those down for the next test, otherwise it's going to be trouble. I know it gets hard because as things go on, you've got to keep up with the other material that's going on too. So, which is the stoichiometry stuff. And we're going to start the U chapter today. But let's take a look at the stoichiometry. Stoichiometry deals with quantities, and we have energy quantity relationships as well. For energy, we have different units. We have the joule, which is the SI unit, the standard unit of energy. It has a physics definition. 1 joule is a kilogram meter squared per second squared times meter. So altogether is a kilogram meter squared per second squared. This has a physics definition. Then we have the calorie. The calorie, which is the lowercase c here. There are two actually. There's one with an uppercase c and one with a lowercase c. The lowercase c one is the chemical calorie. And this has a different definition. The way the calorie is defined is the energy required to raise the temperature of 1 gram of water to 1 degree C. So if you want to increase the temperature of 1 gram of water by 1 degree C, it's going to cost you 1 calorie. To relate the calories and the joules, we have this conversion factor here, which is good to 4 sig figs. 1 calorie is equivalent to 4.184 joules. It's not defined. It's actually 4.1845 joules, or there are more digits here. I don't know why they put it as a definition. It's not a definition. This is the 4 sig figs. And of course, we're going to have kilojoules and kilocalories. Food calorie, this is the uppercase C, is 1 chemical calorie. 1,000 chemical calories here. So these are the typical units. We'll get more practice using these. So we'll come back to this. Calculate the number of kilocalories, calories, and joules in 42.5 kilojoules. So 42.5 kilojoules is at 42.5 thousand joules. So 42,500 joules would be the first. But they're asking us for kcals first. I didn't do it this way. I would do it like this. I just do 4.184, actually 42.5 kilojoules. So we do 42.5 kilojoules, which gets kJ as the abbreviation, and then I convert it to joules. 1,000 joules for every kilojoule. And then I would convert it to calories. Actually, one calorie is equivalent to 4.184 joules. Then I would convert it to kilocalories. It's longer, but it takes us to this conversion factor, the calorie to joule conversion factor. I suppose you could do the kilocalorie to kilojoule since it's the same, so if you're good and comfortable with that shortcut, do that. But I'd like to go back to the basic conversion, which is this. And the thousands cancel, and so we get the same answers. We do. What is the answer? 10.2 kilocalories. That's the correct big. So let me just check that because they don't round. So I want to check the rounding step. So 42.5 divided by 4.184. I get 10.157 kilocalories, which we can round to 10.2 kilocalories. All right, if that's a kilocalorie, then this is equivalent to 10,200 calories. So it's a kilocalorie is 1,000 calories. And then we already know that this is going to be equivalent to 42,500 joules, kilojoules. So that will complete it. Yeah. 42.5 kilojoules is 42,500 joules. In scientific notation, read that. 10.2 kilocalories is 10,200 calories. In scientific notation, read this. We don't necessarily have to convert it to scientific notation. All right, now there's going to be energy involved in chemical reactions, the thermochemical equations. We have something called delta H, delta sub RH. This is the heat of reaction or the enthalpy of reaction. So H is called the enthalpy. This is the change in enthalpy. Enthalpy is the heat content of a chemical system. It's not really, it's the, when we think about heat is a transfer of kinetic energy. It could be a hot object, then we would think of heat content. It could be also potential energy, because typically when we think of heat, we think of kinetic energy, but this heat is used very loosely. It's just the energy of reaction. And the energy of reaction is often given off as heat, or sometimes it's consumed as heat. So anyway, this is just delta H. How are we going to use this? That's probably the most important. How we're going to use it is some reactions are exothermic, some reactions are endothermic. And so the way we do that is like this, ice. If you take ice and you melt it to water, this is an example of an endothermic reaction because energy is going to be absorbed. So if we take ice plus energy gives us water. And so this is an example of endothermic. When we have an endothermic, we can write this as delta H like this. Delta H is greater than 0, which is endothermic, which just means that delta H is positive. If we take water and we want to freeze it, convert that to ice, we have to remove energy. If we have to remove energy, that's called exothermic. Exothermic, delta H is less than 0 here. It's going to be a negative value, so this is exothermic. Thermic and exothermic. So let's take a look at this reaction, the combustion reaction. So this is ethane plus 7 oxygens yields 4 CO2s plus 6 waters. Water should be liquid, so they forgot to write liquid here. Water should be, it makes a difference if water is a gas or water is a liquid in terms of energy, because the energy of liquid water versus the energy of gaseous water are different. Liquid water is lower in energy, gaseous water is higher in energy. But anyway, this is exothermic. It has a negative sign there. So that means heat is released. That negative sign just tells you that heat is a product. Energy, there's no such thing as negative energy in this sense. The only thing is you can either lose energy or you can gain energy. It's like money, Is there such thing as a negative $10 bill? No. I mean, you could either gain $10 or lose $10. If you gain $10, we call it plus $10. If you lose $10, we call it minus $10. But there's no such thing as a minus $10 bill. The same thing with energy. There's no such thing as negative energy. We just gain or lose energy. And so this is merely bookkeeping. That negative sign is bookkeeping, telling us that energy is product here. It's exothermic. In endothermic reactions, energy is reactant. So this would be a reactant here, and delta H is plus. And so the plus tells us it goes on the reactant side, the minus tells us the energy goes on the product side, that's all. We don't typically write reactions like this, or like this. And typically what's written is this reaction with the delta H given, or delta H. The thermal decomposition of limestone, solid calcium carbonate to lime, solid calcium oxide, gaseous carbon dioxide. So they kind of tell us what this is here at this reaction, thermal decomposition. We got calcium carbonate. If we heat this up, this is the symbol for heat, this triangle. It goes to calcium oxide plus carbon dioxide, yeah. What type of reaction is this? Is this a what kind of reaction is this? Well, could it be a metathesis reaction? No. Metathesis ion combination, no. CO2 is not an ion. Could it be a redox? Maybe it's a redox reaction. How can we tell for sure if this is redox or not? In a redox reaction, the oxidation states change. If we look at the oxidation states here, calcium is going to be +2, which is the calcium ion. What's carbon and oxygen? Well, oxygen goes first at -2. That means carbon is what? +4. So carbon's +4, oxygen's -2. Oxidation states are bookkeeping as well. You know, we want to keep track of each atom's oxidation state. Over here, oxygen is -2, carbon is +2. Over here, oxygen is -2, carbon is +4. Actually, this is calcium, sorry, not carbon. Did anything change in the oxidation states? The oxidation states stayed the same. So this is not redox. Not a redox reaction. So if it's not metathesis, it's not redox, it must be what's left over? Acid base. But when we look at this doesn't look like acid base either. But it is. This is what we call a Lewis acid base reaction. Lewis. Really haven't gotten into, but it's a Lewis acid base reaction. Okay, so this required, it's an endothermic reaction. And so what we say is delta H is positive or negative if it's endothermic. Positive, so it's plus 178 kilojoules. If it's positive, which side of the reaction does it go on? The left side or the right side? The left side. So what we could do is we could say calcium carbonate, 1 mole, plus 178 kilojoules yields calcium oxide solid plus CO2 gas. So those are the two ways we would represent this equation. So the first way, where we show delta H off to the side, we don't need the little subscript R. Here. And the second way, where we show it as a reactant. And so what we have is we could do stoichiometry. For every mole of calcium carbonate, we require 178 kilojoules. So if we had 2 moles of calcium carbonate, we'd require twice as much. 3 moles of calcium carbonate, 3 times as much. And so we have this quantity relationship where we can generate stoichiometric conversion factors. The stoichiometric conversion factors are 178 kilojoules required, or 178 kilojoules needed for every mole of calcium carbonate. 178 kilojoules needed for every mole of calcium oxide and for every mole of carbon dioxide. And so we're going to expand stoichiometry by adding these energies. So if we know how many moles, this is our standard mole of A to mole of B. If we know how many moles, then we can figure out how much energy. All right. Either energy required to be input or energy that's going to be output. So this map, what mass of liquid N octane, C8H18 liquid, a component of gasoline must be burned to provide 9.05 times 10 to the 4th kilojoules of heat. Well, there are 2 ways we could do this one. They tell us, take a look at our delta H. There are 2 ways we could represent delta H. If you look at this, this is delta H, but there's no kilojoules per mole. What this delta H refers to is this whole equation. And so we could do the reason we leave it blank like this is because we could relate it to any one of these quantities. And so the conversion factors that we can get are like this. We're going to get calcium carbonate. It would be like this. It'd be 107, well, do it like this. 178 kilojoules per mole of calcium carbonate. And so 178 kilojoules required for every mole of calcium carbonate. But we don't have to restrict ourselves to calcium carbonate. We could say it's going to be 178 kilojoules per mole of calcium oxide, or it's going to be 178 kilojoules per mole of CO2. And so the reason why it's not per mole is because we could have it per mole of any one of those components in there. But they're telling us here it's it's minus 5471 kilojoules per mole of C8H18 burned. So actually, on this particular problem, we don't have to come up with a balanced chemical equation. They say for every mole of C8H18, we're going to get 5,471 kilojoules. And so we need to provide 9.05 times 10 to the 4th kilojoules. So we go 9.05 times 10 to the 4th kilojoules required. And then that minus sign, what does that minus sign mean? Does that minus sign mean produce or consume? That minus sign means produced. And so instead, we could write it like this. 1 mole of C8H18 is going to produce 5,471 kilojoules of energy produced. Now, if I write produce, then I don't need the minus sign because it's telling me that that's going to be outputted. This way I don't get negative moles. Okay, then they're asking about what mass. So I have 8 carbons. That's 8 times 1201. 9608. And then I have 18 hydrogens. 8 times 101 would be 1818. Then add those up. So 114.26. So it's 114.26 grams of C8H18 per mole. C8H18. So the kilojoules produced, moles canceled, that leaves us with grams. So let's figure out how many grams of C8H18 is required for this. So 9.05 times 10 to the 4th divided by 5471 times 114.26. 1,890 grams. 1,890.0 grams. We're allowed 3 sig figs, so I could just leave this as 1,890 grams. C8H18, or I could write it using scientific notation, 1.89 times 10 to the 3rd grams. If I didn't make a mistake, calculated mole mass, let's see what they get. So we didn't have to write the balanced chemical equation because we already had the conversion. We're just doing a mole to energy conversion here. Well, stoichiometry, this is a big topic. Let's take a look at some of the homework problems here. This. Chapter. That was the end of the chapter there. That was the last slide in this chapter. So these are some conceptual ones. You got to make sure you have enough time for study. So maybe it's overly ambitious to ask you to look at all the homework problems. Just do the ones that I assign and try to work on those and look at those. If you do have time, it's quite beneficial to look at more problems than I assign. Just look at the answers. This is just standard. When we look at this, the first step in the Oswald process for manufacturing nitric acid is the reaction between ammonia and oxygen described by the equation here. Ammonia is not on our chart, so the chart method is kind of tough for this one. But here we have ammonia and oxygen, which yields nitric oxide from water. The change in the conditions can change the product, so these types of reactions are best dealt with by the skeleton method. Let's see. But that's the balanced chemical equation, so it's simple. It's a redox reaction. That particular one is. Okay, how many moles of ammonia would react with 95.3 moles of oxygen? And so this is just a mole-to-mole conversion. Ammonia and oxygen react in a 4-to-5 ratio. Just use dimensional analysis to figure that out. So if you look at the first first series of problems. Let's take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9. These are all mole-to-mole conversions here, except now we're getting into grams. So explosion of nitroglycerin is described by the equation here. That's nitroglycerin. The 4C3H5, NO3 threes. That decomposes into CO2, water, nitrogen, and oxygen. How many grams of carbon dioxide are produced by the explosion of 21.0 grams of nitroglycerin? And so here we're going to have to do grams of nitroglycerin to moles of nitroglycerin, moles of nitroglycerin to moles of CO2, moles of CO2 to grams of CO2. And so that's the classic stoichiometry problem. Gram to mole, mole to mole, mole to gram conversion. So we have more problems. So they're all similar. Gram to mole, mole to mole. So grams of A to moles of A, moles of A to moles of B, to grams of B. Okay, then we have a percentage yield problem. What is the percentage yield? So we got to calculate the theoretical yield. And so 8.818 grams of sodium thiosulfate. This would be sodium thiosulfate here. We're going to produce 2.61 grams of sodium bromide. Okay, so this is the actual yield, 2.61. So based on 8.18 grams of sodium thiosulfate, what is the theoretical yield of sodium bromide? Calculate that. From that, we can get the percentage yield. The percentage yield is the actual yield, which would be 2.61, divided by the theoretical. Usually it's less than 100% because of loss. The same thing, this is percent yield. This is a different type of problem here. The calcium cyanamide is a common fertilizer. When mixed with water in the soil, it reacts to produce calcium carbonate and ammonia. So the ammonia part, the calcium cyanamide reacts with water, produces ammonia. Ammonia is the fertilizer part. It gets nitrogen in the soil. That's the reaction here. How much ammonia can be obtained from 7.25 grams of calcium cyanamide in a laboratory experiment in which the percentage yield is 92.8%. So we're going to lose 7.2% of the ammonia. If we lose 7.2%, then we're going to get a little less. So from 7.25 grams, we figure out the theoretical yield of ammonia, and then we cut it down. We cut down the theoretical yield because we lose a little bit. So that would be an example of application of percent yield. This is the same exact problem. It's at 76.6%, so we lose a lot more in respect to the reaction here. This is an 88.8% yield. This is a 71.1% yield. Okay, this is going to be a different problem here, so all of those problems are very similar. 37, calculate the percentage yield in the photosynthesis reaction by which carbon dioxide is converted to sugar if 7.03 grams of carbon dioxide yields 3.92. So this is what we're starting with. This is going to be the actual yield of sugar. And so we have to calculate the theoretical yield. So number 37 is just the same as the previous problems up higher. Again, 38 is a percent yield problem. 39 is another. Well, 39 is different. 39 is ethyl acetate. Ethyl acetate is manufactured by the reaction between acetic acid and ethanol. And so this would be acetic acid, ethanol, that makes ethyl acetate in water. How much acetic acid must be used to get 62.5 kilograms of ethyl acetate if the percentage yield is 69.1? So this is like you want 100 cookies. Well, you better plan on making more than 100 because you're going to lose some. And so if you want 62.5 kilograms of ethyl acetate, you better plan on making more than that because we're going to lose some. How much are we going to lose? We're going to lose about 30.9%. And so you got to make 30.9% more. And so what we do is we use a conversion conversion factor. We did an example of this type of problem in class. This is the same. 40 is the same kind of deal. This is a conceptual thing. You know, if we make ammonia from nitrogen and hydrogen here, you know, we can write the balance equation. And we can mix them in different ratios. So this is conceptualizing which species is limiting reactant. And so this is more conceptualizing here. This is more conceptualizing. And so we have zinc and hydrochloric acid. So it's a fixed amount of hydrochloric acid. So in flask 1, the reaction stopped. There's no more reaction. Can you tell what the limiting reagent is? You see there's still chunks of zinc here. So we must have eaten through all the hydrochloric acid. There must be no more hydrochloric acid left. We have excess zinc. In flask 2, there's no more zinc left. And the balloon has reached the same size as the one on the left. And so flask 2 is what we call stoichiometric. Balloon completely inflated, no zinc remains. So we just added just the right amount of zinc because all the zinc reacted and all the hydrochloric acid reacted. We can tell all the hydrochloric acid reacted because the balloon is the same size as flask 1. Flask 1, all the hydrochloric acid reacted. In flask 3, all the zinc is reacted, but the balloon isn't as big. That means there must be some hydrochloric acid left over. So this is excess zinc. This is excess hydrochloric acid, and this is stoichiometric here. So those are just conceptualizing problems with limiting reagent, excess reagent. Okay, we can tell when we have a limiting reagent problem because we're given more than one reactant. You know, in the previous problems, we're just given one reactant, we just calculate the theoretical yield. In this particular one, we're given 1.63 grams of barium chloride and 2.40 grams of sodium chromate. And so we have two reactants. Automatically, that's a limiting reagent problem. So we have to calculate the yield of product from the barium chloride, and we have to calculate the yield of product from sodium chromate. They tell us what chromate is, but I expect you guys to have it memorized. Everyone should have chromate memorized. So I'm not going to be as generous as they are as far as nomenclature. So you're going to have that for Chem 1A. All right, 46, it's the same thing. We're given carbon dioxide and potassium hydroxide, 15.6 grams, 43.0 grams, so it's a limiting reagent problem. We calculate the yield. We use the smaller amount method. 47, same thing. 48, same thing. 49, same thing. 50, same, all limiting reagent problems. Okay, then we go on to 51, and these are energy conversions here, kilojoules. So we do kilocalorie to calories, calories to joules, joules to kilojoules. That's how I do it. How many calories? 651 joules. I just go joules to calories. Determine the number of kilocalories is equivalent to 6.22 times 10 to the third joules. I do joules to calories, calories to kilocalories. So here's some more. Joules to calories, calories to kilojoules. That's weird. I do joules to kilojoules first, and then joules to calories. Calories to joules, and then joules to kilojoules, that's fine. Kilojoules to joules, joules to calories, that's fine. So just energy conversion using the conversion factors. When 15 grams of carbon is burned, 493 kilojoules of energy is released. Calculate the number of kilocalories. So this is just kilojoule to calories, calories to kilocalories. 54. A list of calorie content of foods indicates that a piece of lemon meringue pie contains 333 calories. Note this calorie is capital C. This calorie is lowercase c. So these are different. One capital C calorie is 1,000 lowercase c's. Like say, for example, if you have a 600 calorie meal, let's say, 600 calories in chemical sense would be 600,000 calories. So nobody wants to have 600,000 calorie meal, right? And so this is why they changed it. Rather than saying kilocalories, they just made this capital C. So in reality, that's 333,000 calories with a lowercase c. Each day, 5.8 times 10 squared, so 580 kilocalories of heat is transferred out of the body by evaporation. How many kilojoules are removed in a year? Well, this one is a dimensional analysis problem from before. And this is the one where we're going to change both the top and the bottom. So sometimes we'll have ratios that we change. So this one's a little bit different than the other problems. So let's take a look at this one really quick. Do that. And so I got 5.8 times 10 squared kilocalories per day. And so I can make a ratio like this. And so what they want is how many kilojoules are removed in a year. So I want to go from kilocalories to calories. 1,000 calories per kilocalorie. And then calories to joules. 4.184 joules. You don't have to memorize that per calorie. I'll give you that. And so that gives us joules, but we want kilojoules on the top. And so for every kilojoule, we have 1,000 joules. And so on the top now, we have kilojoules. Kilocalories cancel, calories cancel, joules cancel, leaving us kilojoules. Now on the bottom, we don't want days, we want years. And so we can do this, 365 days, we'll write on the top per year. And so the days will cancel out. That'll give us kilojoules per year. Let's see what they got. It's 8.9 times 10 to the 5th kilojoules per year. Again, they can combine this conversion. I'd like to keep it spread out because I'd like to come back to this one here. Okay, now number 56 is another ratio like this. Burning sucrose transfers 3.94 times 10 to the 3rd calories per gram to the atmosphere. So we get calories per gram rather than calories per mole. This happens a lot for sugars because people want to know how many calories per gram. Also for fuels, because different fuels weigh different amounts. And so they want to know how many calories per gram of fuel you get. In this case, the fuel sucrose or sugar. Sucrose is table sugar. So for every gram of table sugar you burn, you get 3.94 times 10 to the 3rd calories to the atmosphere. Calculate the amount of energy in kilojoules transferred from 56.7. So this is just dimensional analysis. Grams cancel grams, and then you're left with calories. We use that as a conversion factor. Energy is transferred from sunlight in the photosynthesis reaction with carbon dioxide and water combined to produce sugar. It's a different kind of sugar. Table sugar, sucrose, is C12. This is glucose, which is C6. And release oxygen. The amount of energy is 2.82 times 10 to the 3rd kilojoules per mole of sugar formed. So they tell us for every mole of sugar, we're going to require 2.82 times 10 to the 3rd kilojoules. So the reaction is endothermic. Photosynthesis is endothermic, converting energy from sunlight to, and they're saying energy stored in the bonds. And the energy stored in the bonds is called potential energy. thermochemical equations may be written in two ways. Okay. So we can write this one. We'll just start off with CO2 combines with water. Yields C6H12O6. So this is a photosynthesis reaction here. CO2 is gas, C6H12O6 is a solid. Just sugar. And so we have, let's take a look, and one more product is formed. Plants produce oxygen gas. And so I have 6 carbons here. I'll need 6 CO2s. I have 2 hydrogens or 12 hydrogens. I'll need 6 waters. That's going to give me 12 plus 6, 18 oxygens. I have 6 here. I'll need an additional 12. So if I do 6 there, I'll get 12. So this is the balanced chemical, but we're doing thermochemical. Now, is this endothermic or exothermic? Well, it's endothermic. So if it's endothermic, it's going to equal plus. If it's exothermic, we change the sign to minus. But this is endothermic, so it's 2.82 times 10 to the third kilojoules. Right? Or the other way of writing it is we've got to write it 6 CO2s plus 6 H2O, liquid, gas, plus 2.82 times 10 to the third kilojoules is going to produce C6H12O6 plus 6O2. Yeah, this is solid. The states are very important in thermochemical equations. The states are very important because, you know, if you take a solid and convert it into liquid, does that require energy to melt or release energy to melt? It requires energy to melt. And so if it's a liquid, it's a different energy level, we call it. And so the states are very important here. What kind of reaction is this? Is this metathesis? No, it's not metathesis. There are no ion combinations. Does it look like an acid-base to you? It doesn't look like an acid-base, but it might be one of those tricky Lewis acid-base reactions. But when we look at it, do you know what kind of reaction this is? Is it redox? Well, immediately I can tell that this is redox. How can I do that immediately? Because oxygen over here, what's oxygen here? -2. Oxygen here is -2, but oxygen here is 0. These oxygens are -2, so nothing happened with these, but this oxygen is 0, so something happened. This is a redox reaction. Photosynthesis is a redox reaction. All right, so 58 is very similar. You know, when gaseous nitrogen reacts, you know, gaseous, that's just another thermochemical equation, so we got to just write the balance. They tell us the product, so we don't have to do any prediction. You know, if they tell us the reactants and they tell us what the products are, then all we have to do is balance. So all these are the same. All these happen to be redox, it looks like. But they don't have to be redox. Different kinds of reactants.